So I said to the guy, that's not a Cheeto, that's Grandma. Welcome back to another exciting chemistry video. Today, our focus is going to be on stoichiometry and a brief introduction to titrations. Now, we're going to go through stoichiometry fairly quickly in this video. If you need a more broken down version of stoichiometry, feel free to watch maybe my Chemistry 2 video or my Chemistry 1 video, so that way you can get a real in-depth perspective on stoichiometry. We're not going to do it fully We're not going to fully do it justice today, but rather we're just going to have a brief overview and reminder of how to go through and do stoichiometric calculations. I always say that it's not something that you can go through and just memorize. Rather, it is a mindset. You have to look at the pathway between where you're starting and where you're ending. And then we're going to wrap up today as well by doing a brief introduction to the concept of titrations. Now, you may have done titrations before in other chemistry classes. We'll just talk briefly about what the process entails, how it works, and how it can be used in stoichiometric calculations. So without further ado, let's go ahead and get started. So let's go ahead and look at our student learning objectives. There are not very many student learning objectives. However, they are very important to understand and master. So first off, we need to be able to perform any and all stoichiometric conversions using molar mass, number of atoms and moles. Perform any and all stoichiometric conversions using ideal gas law and molarity as conversion factors. And finally, explain a titration and how it can be used to find the unknown concentration of a solution. So again, not very many student learning objectives today. However, they are very important to your success in this course. Let's go ahead and get started. Let's talk a little bit about reaction stoichiometry, which involves determining amounts of reactant and product from known amounts of substances. So we go back and reflect on all of the different types of conversions that we have talked about previously, such as molar mass, being able to convert between grams and moles, and Avogadro's number, which has the ability for us to convert between atoms, molecules, particles, and moles. One thing we're going to be looking at here is a mole ratio, which allows us to convert between different chemical species. The mole ratio is determined based on the coefficients of your balanced chemical equation. So you should be able to convert between any substance in any chemical equation by utilizing the mole ratio. If we look over here on the right, we have a reaction of magnesium nitride and water to form magnesium hydroxide and ammonia gas. We take grams of ammonia gas and convert it to moles utilizing molar mass, which is found on the periodic table. And then we will use the mole ratio to be able to convert between moles of one substance and moles of another. Going through moles is the only way that you are able to go through and convert between two different chemicals. And again, don't forget Avogadro's number, which is 6.022 times 10 to the 23rd atoms, molecules, or particles in 1 mole of something. Again, any derived unit can be used as a conversion factor, as you'll see in the next slide. So again, just as I reiterate, any derived unit can be used as a conversion factor. So we can use Avogadro's number to convert between atoms, molecules, and moles. Density is a derived unit. That allows us to convert between grams and a known amount of volume, milliliters, liters. Mole ratio, mole to mole conversions. A few more that we'll talk about that maybe we haven't looked at previously will be something like enthalpy, which we can use to convert between kilojoules and moles of a substance. Molarity, which is again how we measure the concentration of a solution, moles per liter. Or gases that are at STP, which is standard temperature and pressure. 1 mole would be 22.4 liters. So again, any derived unit can be used as a conversion factor. So you may want to think about these as tools in your arsenal to be able to convert between one unit and another. It's not just always going to be grams, moles, atoms, and molecules. There are lots of different units that we can convert between, and we can do that as long as we have a derived unit that is equivalent to one another. Now, limiting reactant is a concept where we were given two initial amounts of a substance. A reaction is only going to continue until one of those two substances has been used up. So if I look at the example on the right here, I have 4 molecules of hydrogen and 3 molecules of oxygen. Well, we can only make as much water as one of those reactants limits us to be able to do. So as a result, all of the hydrogen gets used to make water, but there's 1 oxygen that's left over. If I run out of one reactant or the other, the reaction completely stops. We can't go forward with the reaction. So when you're doing stoichiometry problems and starting with 2 different amounts, you're going to see how much product you're going to produce from both of those reactions. The amount that produces the lower amount of product is going to be your correct answer. And the reactant that produces the lower amount is considered limiting. The opposite is considered excess. So we really need to make sure that when we're given two initial amounts of a substance that we convert both to product, and then once both are converted to product, the one that produces the lower amount of product is going to be your correct answer, and the reactant that causes that is considered to be limiting, while the other reactant is said to be in excess. We have some amount of that reactant left over. Now we can use stoichiometric principles in gas problems as well. Since the ideal gas law contains moles, it can be used to solve problems for gas stoichiometry. So in the example that is given on the right-hand side of your screen here, it is asking how many liters of CO2 at 25 degrees Celsius and 745 millimeters of mercury can be removed by 1 kilogram of sodium hydroxide. So if I look at that reaction, I'm given a temperature and a pressure, but in order to be able to solve for volume, I'm going to need moles for my ideal gas law. Well, I'm not given moles. I'm given kilograms, and I'm given kilograms of something else in the reaction. So I need to convert kilograms to grams, grams to moles of NaOH, use the mole ratio to convert between moles of NaOH and moles of CO2, and then plug that into my PV equals nRT equation in order to be able to solve for it. So, like I said, there's lots of different ways that we can go through and approach these problems. Like I've said before, this is a process that you need to understand. There's really no way to go through and memorize how to do these types of calculations. So knowing where we're starting and where we're ending is very important as you go through and complete these types of problems. Let's look at some sample problems and see where we can go. How many grams of lead-4 carbonate are needed to completely react with 200 milliliters of 1.342 molar nitric acid? The products of the reactions are lead-4 nitrate, water, and carbon dioxide gas. So the very first thing we need to do when we are performing stoichiometry problems is to make sure that we write out a full and balanced chemical equation. But even before then, what we want to do is we want to make sure that we know what information we are going to start with and what information we are going to end with. So we are going to start with 200 milliliters. We very rarely start with a derived unit, and remember that molarity is moles per liter. So we're going to start with 200 milliliters of our nitric acid, and what I need is grams of lead carbonate. So again, the next thing I'm going to do is go ahead and write my balanced chemical equation. Make sure you completely go through and balance it appropriately, so that way you have the correct coefficients for when you do the mole ratio. So let's start with 200 milliliters of HNO3. We then are going to convert milliliters to liters, and then I'm going to convert liters of HNO3 to moles of HNO3. Remember that we can use molarity as a conversion factor because it is a derived unit. Once I get moles of HNO3, I can then go and convert that to moles of PbCO3 using the mole ratio of the balanced chemical equation. Once I am done with that, then I can convert moles into grams. Now, if you're a novice of stoichiometry, you haven't done this process before, a key thing to remember is that whatever unit is on your previous step needs to go on the bottom of the next step. That's going to help your units cancel as you go through and conduct these types of problems. Also remember that the number of significant figures that you are going to use at the very end is the same as what you start with in your problem. So again, this is one of those skills that if you aren't really sharp on this, go back and check one of my other videos, but really understand that we can use a variety of different derived units as conversion factors. Here we use molarity. We can use, again, density. We can use enthalpy. We can use a whole bunch of the different derived units. So just make sure that you're aware of that. And it's also really good to make sure that you know your basic conversions, you know, milliliters to liters, know your metric prefixes, and know how to convert between them. So here we're taking a look at another stoichiometry problem. According to the reaction above, what volume of NO2 is produced from the combustion of 100 grams of NH3, assuming the reaction takes place at 25 degrees Celsius and 1.03 atmospheres? Well, the first thing, again, we need to do is to take a look at what we are going to start with and where we are going to finish. So I have 100 grams of NH3. That's where I'm going to start, and I need liters of NO2. So because I need something out of the ideal gas equation, I am going to utilize that last. And then the very first thing I'm going to do is take that 100 grams of NH3 and then convert that to moles of NO2, because what we're looking for is the volume of NO2, so I need to convert that to moles of NO2. So again, we start with 100 grams of NH3, grams to moles of NH3, and then moles of NH3 to moles of NO2 utilizing the mole ratio from your balanced chemical equation. What I end up with is 5.87 moles of NO2. The next thing is that now I'm going to plug that mole number into PV equals nRT, because I have moles, I have temperature, and I have pressure. So now I can go through and solve for volume, which would be 139 liters. So again, mental flexibility is important with this. I think it's really important to know where you're starting and where you are going. Knowing that really helps you build up the roadmap to be able to go from what you're starting with to where you end the particular stoichiometry problem. So again, mental flexibility, very important in these types of chemistry problems. Now, titrations are great ways to know and find unknown concentrations of solutions. What we do is we take one solution of a known concentration, that's known as the titrant, and we use that to find the unknown concentration of another. Now, this is really frequently used in acid-base chemistry. It can also be used in redox or reduction oxidation reactions. And again, we'll talk more about those as we approach those particular units. I just want you to understand the real basic of this. Now, if you've done this before, you may remember this as the reaction where you have the long burette. You add a little bit of it very, very slowly until it turns pink. And the reason it turns pink is we use a pH indicator, and typically when it turns pink, we can safely say that the moles of acid is equal to the moles of base. That is known as the equivalence point of the titration, where our moles of titrant are equal to our moles of analyte. So if we know the volume that we added, we can then determine the concentration of the unknown by utilizing a simple dilution calculation or some simple solution stoichiometry. Now, the endpoint is typically indicated by a color change. The type of indicator that we use is dependent upon what we are titrating. So if we know that our equivalence point is really high, we might use something like phenolphthalein, or if it's something that's in the 12 to 13 range, we may use a different pH indicator. But these change based on where the solution is on the pH scale. Now, the equivalence point is not necessarily the same as the endpoint. The endpoint of the titration is when the color changes. So notice that if we are doing something where we end up with a pH of 7, that we can actually use phenolphthalein even though its pH change, or the color changes at 8.2, because notice the volume of the sodium hydroxide that's added. The difference between where it is at a pH of 7 and a pH of 8.7 is very negligible, so we can use phenolphthalein. We probably would not want to use methyl orange, only reason being is that it tends to turn a pH kind of a little bit to the left of the 25 milliliters, so we probably would not use that, but using litmus, using phenolphthalein would be perfectly fine. So again, we'll go through more detail on titrations as we approach our acid-base unit and our redox unit. So hopefully you got a lot out of this. Again, make sure you're able to perform any and all stoichiometric conversions. These should be things that you've been doing for the last 2 or 3 years. You should be in real good shape on this, but just understand that any derived unit can be used as a conversion factor. Also, make sure you understand the basic concept of titration and how that can be used to determine the concentration of an unknown substance. Thanks for watching the video. I hope you enjoyed it. As always, if you have any questions, make sure you let me know. Like, comment, subscribe if you can, and have a great day. We will see you soon. Bye-bye.